Zero tolerance for another episode of Learn to Burn. Today's topic is going to be the challenges of mold making. I want to talk about how this trode came to be the way it is. Mike will get into the details on it, but this is a combination of three different tool makers' suggestions as to how to achieve these features. And all these features that you see right now, this is literally a quarter of what's needed for the job, and I'll let Mike get into the details on this electrode, as you'll hear in just a minute.
We'll start it here. So this is roughly a 5x5 electrode with approximately 5,000 forms standing on it. And the forms are so small that we cannot apply overcut or get a cutter in between here without crashing into the next feature. In order to solve this problem, we eliminated every other form in both directions on this electrode. What that allowed us to do was to go with a much larger, more robust cutter that would fit in between here, apply overcut to the form without damaging anything else. So you see, this is the first rotation in green. The pink is the unfilled spaces. Second rotation, third rotation, fourth rotation. This completes the entire form and still allows you to cut the electrode with a cutter big enough to make some time on it.
I can't see anything.
Ooh, I don't like it.
Smells like good.
Take it on. Alright, we're at the first stage of this 4-stage electrode. This is going to actually give us a real good way to make these tiny little features all in one electrode, but we have to burn it in 4 places, so it's acting like 4 separate electrodes. It made it fast to cut, like way faster, like a third of the time, and it might take a little longer to burn, but we're going to have a lot better results and more efficient. So this is a real challenging type of burn for a very simple shape. Here's a test cut trode that we made, and we determined that this was going to take way too long with too many cutters that would potentially wear out. So that's why we changed our method. Okay, we're here with this really tiny electrode pattern that we put in. It was looks like a really good success. We're gonna take a look. It's a 45-hour burn that we've got there. So let's take a look real close. I'm gonna blow this off and see how it looks. I'm gonna move this head back so we can see the light a little bit better. And I'll continue to blow this off and really get a good look at it. Now, inside here, I don't know if we'll be able to fill this with plastic very well, but we're gonna do the best we can. Depends on how well it packs it and fills in all those sharp corners. cleaned up, we'll be able to see better. I do want to point out some little tiny damage that we see as a result of the higher amps we were trying to push through it. You see these shiny areas? It actually, the arc that was created from this electrode with all the power, it actually made a circle area, and I can't hold this very still, but I just want to show you. You can see the shiny areas where it looks like it's slightly damaged a little. We actually may have to take this block and grind maybe a half a thou or a thousandth off of it to make that clean up. But it's very little, but if you have those settings wrong, that's what can happen. That's a challenge of building molds and making stuff that's never been made. So very cool. You've seen that we were burning this job already. All those little features, the little pyramids. There's literally over 5,000 little pyramids that end up forming this part. And what we found is that the electrode wore more than we wanted with 2 electrodes. So we're taking it over here and we're making another electrode, the same electrode, and we're literally dropping it down to give it brand new features so that we'll have a fresh start and try to get the depth we're after. I know this is kind of loud, but part of the trick, part of the challenge of this part is that there are so many features and it doesn't leave us a lot of room for the cutter, which Mike had already explained. So getting it to do what you want, sometimes you have to make more than you were anticipating, and it actually costs you a little bit of time, a little more money to do it correctly. But in the end, we'll end up with a very good part and a happy customer. So we've learned a lot from this job and this little feature that was a big challenge to make efficiently and get it burned properly. All right, we're here with our mold that we just finished running, and this was a big giant slug that had to be wired, and Ethan actually wired this out, and it is actually this block, and we have an insert in the back that has a whole bunch of features on it. And the reason I want to talk about this is that part of the challenge of building molds is not everything goes the way you want it, like most things in life, but this job was particularly challenging because we're using aluminum, we're making an outside housing for a consumer good, and when we were going to do the finish on this job, we had to sandblast the inside of this part. And when we did that, we actually mushroomed over the aluminum and it created a die lock condition. And once we did that, we molded some parts, our part snapped off and got stuck in the cavity, which was absolutely horrible. We had to take the whole tool apart and then find out what was going on. We couldn't figure out what was happening when there's so many features inside here that the part should have stayed onto on the core side. So we had to take it apart, and we actually dug into it and found out that we mushroomed over the features, and that ended up making 1,000 little undercuts that held the part on and literally broke it into pieces like this. So once we were able to get those features all straight and draw, we were able to make good parts. And the good parts turned out like this. So being able to overcome a situation that looks really bad and make it turn out good, that's the whole idea of being a machinist, making molds, anything that you're dealing with in a machine shop world. You have challenges and you overcome them. Some custom blades that we have to make for a job. It's very intricate and I'm not real happy about it, but we are going to tackle it because that's what the customer is after. If you look at these parts, they're after a blade that looks like this, and it's not real fun to make these. So unfortunately we got 3 different sizes that we're going to make, and this is the block, and we're going to have Ethan explain the method to the madness and how he went about doing these.
Those blades that Steve was mentioning. Now, as you can see, these are only 32 thousandths thick. So we got a lot of flexing and a lot of warping that can happen with these. Now the method that I went through it, which can pertain to some people but not others, is I went about it in a way where if you don't have somebody available to do, say, bench work on these, because there's always going to be the EDM tab left over on it, if you don't have somebody to take care of that bench work for you, what you'll notice I did on this block was that for each blade, there's two holes, two start holes from this EDM drill. And the reason behind that was because since these are so small, over such a great distance, that if we were to use only one holding tab, it would have to be a larger size to keep the part from shifting due to flex and stress material. That's great, but then you're going to have a much larger tab that you're going to have to deal with that's not going to be as accurate as the rest of the part. So the theory behind this was to create two tabs to support the piece so that it didn't flex, but also those two tabs only being 0.008 wide. That allows there to be a very, very small witness mark left over. Now, this is still not the preferred way most of the time. I was doing this on an extreme rate because, again, I was pretending there wasn't going to be any afterwards finishing. So I'm trying to make sure the surface is perfect the entire way through. So what I had to do, though, when it came time to cut off the tabs, is you'll notice we have a lot of dried up glue here, and also there's some brass shims still inside the workpiece. What I had to do before we cut the tabs was I had to take brass shim and shove it between the gaps that the wire created during its rough and skims. That way, the brass not only held the part in the block still when the tabs are cut off, but it allowed continuity to flow through, because once those tabs are broken off, there's no way that there can be any grounding action and you wouldn't be able to get the tabs burnt off. But then adding the glue on there was also another way to sandwich the pieces inside the workpiece so that the flush pressure wouldn't necessarily break them free. Again, it was a little bit more of a finesse process. If you do have the ability to have a bench hand or even a precision surface grinder take care of the tabs, I would go for that. But in extreme cases, this is just one method how you can deal with extremely thin and also long workpieces. So we have a test block in here just to give you a demonstration of it, and if you were to get a little bit closer to it, you will notice that I actually did put it on an angle, so you can tell that we're not going to be cheating here, but we're actually going to be showing this. So this is a great function of the Mitsubishi, is that it's going to be able to pick up this piece using a nice sidewall, which that is key. You don't want to use anything wavy or anything from a rough cut. A good pickup wall, ground surface, is going to be your best. But I don't have to use my indicator. First thing that you want to take note of is the position of your workpiece, but also the position of where your wire and your head are. Because on the monitor, there's going to be several selections that you need to make that are position orientated, so that your axis rotation value is going in the correct direction. Now, there's a few ways to do this, but I'm just going to show you one of the ways that I prefer, which you might have to go ahead and turn on a couple switches on your machine. So for example, in your machine setting, Auto 3, if you turn on multiple work and work alignment advanced, you'll be able to follow these steps exactly. Even if you don't normally work in this switch on state all the time, it will at least work for this function. Because again, I'm only going to show you just the one way for today. So once these two switches are check marked and you return to your home screen, I recommend putting the relative menu on top and then actually program position and then choose a work offset of your choice. It doesn't matter if it's G54, 55, or any of the W's, but this is what the angle value is going to be set to. So, while we're in our work setup page, workpiece pickup, on the very far end is the black magic that a lot of people don't mess with, the work slope. Now, like I was saying before, the orientation of your part and the wire do matter. So in your drop-down box, which is the wire start point, you want to look for the picture that is the same setup as what you have. For example, ours would be number 5. Our wire is on the Y negative of the part, and we are starting in X negative and will be moving to X positive. After that, you just simply set the distance that you want the wire to travel over the piece. Again, the more distance you can set, the better, it'll be more accurate. For this demonstration, I'm just going to do 0.5. And let's make sure that you set your value to axis rotation. Axis rotation is how the machine skews its axis in degrees. Angle K is rotating the program. So we won't go too deep into that, but the main thing is to just set axis rotation. After that, we can just hit start. Now on the screen, we can see that it actually gives you the resulting degree at which that workpiece was offset on the table. So we're almost at 5 degrees. So now the cool thing is that your relative system is now switched with the machine to that rotation angle. The machine has comped all its axis to actually make that 5 degrees seem like it's on 0 for you. To kind of give you what I'm talking about, if you switch one of the menus over to the actual machine position, which is reading off of the glass scales, you will notice that the machine position will move, but the relative will only move in one axis. For example, let's move an X positive, and you'll notice relative only the X will move, but machine position has both axes. So the theory behind this is to just pretend that you're working with the machine like normal. Don't try to remember all the trig or you're skewed off of 5 degrees. It's basically saying, I've rotated my axis for you and it's taking care of it. Now again, it is very important, I can't stress this enough, to make sure that you do set the correct orientation of the work slope wire start point. If you don't do that and you're going in the wrong direction, it will actually skew the way the degrees are. I mean, 0, the 90 degrees, the 180, it can all depend on where your wire is at. So you must make sure that that is set, and for this demonstration, those 2 switches in machine settings were on, how we had them for this. Now, to actually show you that it did work, granted, there might be a little deviation because I only went over about a 1/2 inch. When I zero my indicator on this wall and run it in X positive, it should show 0 because the machine has skewed to the part. This could be a great function for details that are very hard to align, or actually very fragile features where you can't use, say, a brass tap or manually move it around. You can just let the machine pick it up. The last thing that I do want to stress, though, is because those 2 switches we turned on, when you are done with the program and you no longer need to run the part on this angle, you must make sure that you clear the axis rotation value so it doesn't carry over onto your other jobs. Now, the most foolproof way to do this is you actually go into the work offset table and you find the program or work coordinate position that we set it to. For example, mine is W01. If you go all the way over to the side, you see that's where our AR value is saved. Now, by zeroing that out, the machine is back to exactly how it was before you did the work slope pickup. So now you can return to your jobs as normal. Just remember the couple things we talked about. The wire start point, making sure the 2 switches were on, and also when you're done, you want to make sure that AR value is cleared, and then you'll be able to carry on and do what you need to do.
Thank you for joining us for our episode of Learn to Burn. I hope you enjoyed it. I hope you got something out of it. Remember to subscribe and like, and any comments and questions, we'd love to hear them. Thank you. Talk about, come on.
You're done now.
Come on, no, we're good. Talk about,
I didn't do that.
you didn't do that. I want to talk about.
So these are these tiny blades that we had to make. I was doing good.
I hope you enjoyed today's lessons, tricks and ticks and bugs and dogs.